Hello everybody from Tokyo, Japan. So I'm going to be kicking off this ACI-JCI prequel to the fifth joint session. My name is Michael Henry from the Shibaura Institute of Technology, located in the center of Tokyo. And today I'm going to be talking about the evaluating the sustainability of concrete with multi-criteria analysis. Now, this is, of course, a very pressing and very timely topic because, as many of you know, now a lot of the organizations around the world, including ACI, and we'll hear a presentation about this later, FIB, and of course in Japan Concrete Institute, Japan Society of Civil Engineers, and so forth. All of these organizations are now very actively moving towards how to include sustainability, how to reflect sustainability in design codes and specifications for concrete and concrete structures. Now, unfortunately, there is not a lot of precedent. There is no standard methodology for how to do this. If we look at ISO, for example, well, there are some standards that we can refer to, like the ones shown here. However, these are mainly focusing on just the environmental impact. But as we are all aware, of course, sustainability goes just beyond the environment. And so this means that we have to think about not just environmental impact, but social impact, economic impact, and how we bring these different performances together. So commonly or traditionally, we would say that for the design of concrete structures, of course, we need to meet performance requirements. These would be things such as durability, safety, usability, restorability, third-party impacts. And these typically then are balanced against the economic performance, typically the cost, initial cost, life cycle cost, and so forth. And then so try to meet performance requirements while minimizing cost. But if we introduce sustainability into this equation, the decision-making becomes much more complicated. Sustainability performance can be very complex. And of course, it depends on how we define sustainability, how we define our boundary conditions, what we choose to reflect. Commonly, of course, we see CO2 emissions are usually referred to as one of the primary and are often used in one of the primary environmental impacts that we consider to reflect the environmental sustainability. Resource consumption, waste generation, and so forth are a few of the other ones. Of course, there are social impacts as well, health, safety concerns, and so forth. But now that we can see that not only do we need to meet performance requirements, try to minimize costs, but we also want to try and minimize these environmental impacts and generate as much sustainability value as possible. So what this means is that as we start to reflect sustainability performance in a concrete design, the decision-making throughout the life cycle process is going to become more complicated. It's going to be driven by an increasingly numerous and diverse performance criteria. So this is then the launching point for looking at the multi-criteria analysis. So multi-criteria analysis, or we could also refer to it as multi-criteria decision analysis. This is a set of methods developed by operations research, belongs to the operations research field. And it's simply, at its core, it's a set of methods used to compare alternatives in some sort of decision. So this doesn't have to be just sustainability or concrete. However, from past research in the sustainability field, multi-criteria analysis has been suggested as perhaps one of the most appropriate and useful tools that we have available to us to carry out sustainability evaluation, to determine the sustainability characteristics of different decision alternatives, and then use that as quantitative evidence to make a decision. This is because sustainability itself is multidimensional and quite complex. And as I showed, when we introduce sustainability, this ends up introducing additional criteria that we need to consider. So multi-criteria analysis can help us handle these different criteria. So the goal then of multi-criteria analysis is to quantitatively evaluate a set of alternatives to provide evidence data for comparison and to support decision-making. So in the case of sustainability evaluation, we can find that this MCA can be particularly useful because we can use it to aggregate multiple indicators into a single index or composite indicator. So if we have a system and we break this complex system down into subsystems that we can represent with individual measurable indicators, at the end, then we need to bring these indicators back together. We want to make a judgment about the behavior of the whole system. So this is one way that MCA can be very useful. So some examples of techniques that have been used for sustainability evaluation that we can find in literature Analytic hierarchy process is one of the main ones that's very popular, and we can see examples of it even in the concrete field. Compromise programming, decision envelope analysis, multi-attribute theory. TOPSIS is also, we can see a lot of examples of using TOPSIS for sustainability evaluation, and there are many, of course, many other options. However, in general, we can say that the steps of the MCA are like this. We have indicator selection, data treatment, data normalization, indicator weighting, aggregation, and then an output, which would be a rank or a score of these different alternatives. So we're going to take a look at each of these steps. Indicator selection step is quite simple. This is the first step where we choose which indicators, what criteria we're going to use to evaluate our decision alternatives. And so this may be affected by a variety of factors, including what is the target of the analysis, the conceptual framework upon which we are basing our decisions, and so forth. And there are different ways that we can go about carrying out this indicator selection, such as top-down or bottom-up. One of the most important aspects of indicator selection, though, is representativeness. How can we choose a holistic enough, a comprehensive enough set of indicators while still keeping the analysis manageable? So this is one of the issues that we have to consider. So next is data treatment. This has some relation to indicator selection. And when we are looking at the data, we need to think about the data quality, data structure, and missing data, and how to handle these three different characteristics. So the next step is data normalization. So typically these indicators are going to be existing on different scales, and they may have different units. However, for constructing a composite indicator, for bringing them together, comparing them, we need to put them into the same dimension and make them comparable. So data normalization is this technique then where we can convert the data and use it to be able to compare disparate indicators that may have different characteristics. We can also use this to compensate for directionality. For example, some indicators, as they increase, they have a positive effect, such as a higher safety factor, for example. This would have a positive contribution to sustainability. However, some indicators like environmental impacts, like CO2, these have negative directionality, meaning as they get smaller, it benefits sustainability. So we can also compensate for directionality. And then there are different techniques which we can use to do this. The next step is indicator weighting. This is a very important step and also can be quite controversial. This is a step where we apply different weights to the indicators in order to reflect the relative importance of these indicators towards the decision. But this is quite a subjective stage. And so we need to be very careful about what is the process whereby we go about deciding and applying these indicator weights. So finally, we have aggregation, and this is where we take these individual indicators and we condense them into a single value. This has some benefits in that it's difficult to see the behavior of a system when we're looking at 10 or 15 different indicators. If we have just one indicator, it's easier to make some judgment about the state of the system. However, we lose the underlying data information when we convert to a composite indicator. So this is a trade-off when we use individual indicators versus a composite indicator. And so we also have to think about compensability. For example, do we allow a certain increase in the CO2 can be offset by a certain increase in cost? So these are things that we have to consider at the aggregation stage. And the next, finally, from this process, then we have the output, which is what we use to support decision-making. And this could be a rank of the alternatives, such as a ranked first, second, third, fourth, or it could be a score on some sort of continuous scale, like 0 to 10 or 0 to 100. And then we can use those values to make the judgment as well. And so then this information can be used to support decision-making by comparing the alternatives. Okay, so these then are just the individual steps of the multi-criteria analysis. And so in order to make this a little bit clearer and to see how we can apply multi-criteria analysis to sustainable decision-making for concrete, what I'm going to do is share a demonstration evaluation applying MCA. And in this demonstration evaluation, our decision objective is to determine the most sustainable concrete mix. And in this case, however, in order to be comparing mixes that have equivalent performance, what we have done is set these decision alternatives have to meet a minimum performance requirement. In this case, our minimum performance requirement is they should have a strength of 30 megapascals. We can, of course, add other requirements of flowability. Of course, because the fresh properties of concrete are also going to be critical, durability, and so forth. However, just for this demonstration, we are just comparing mixes with equal compressive strength. And well, how are we getting these different alternatives? Well, down here we have the mixed proportions of 6 different concrete mixes. These all are meeting this 30 megapascal strength at 28 days, as shown here. And what we see is that it's varying. One is the mineral admixture type. So the first 2 mixes are using just ordinary Portland cement. These second 2 mixes here are using a little bit of fly ash. And the third set, the last 2 mixes here are using some blast furnace slag. Additionally, we also are replacing 100% replacement of normal aggregate with high-grade recycled aggregate as well. So this then allows us to generate these 6 different mixes. And what we can do is we can see the effect of mineral admixture, or the usage of these different mineral admixtures, or the usage of high-grade recycled aggregate on the sustainability evaluation. And so this is these are the different alternatives. These 6 alternatives are what will be looking at in this evaluation. So this is the setup for the indicator-based sustainability evaluation. So we chose a set of 14 quantitative indicators. We use a statistical normalization, an equal weighting, linear aggregation, and then the output will be a single ranking or a single score. So this is a deterministic evaluation output for a single analytical scenario. So this is an indicator set. These are 14 indicators, which were taken from an indicator framework, sustainability indicator framework for concrete, which was developed by myself and my student. So anyway, this is some of the examples. So we have energy consumption, raw materials consumption, recycled materials consumption, water consumption, as well as various emissions, CO2, SOx, NOx, particulate emissions, and then some impact category indicators such as global warming potential, acidification, eutrophication, et cetera, et cetera. Over here is information such as which SDGs these indicators are related to. Next is conceptualization. So this is a kind of a sub-step of the indicator selection. It's how we decide the structure of the indicators and how they load to our goal. So in this case, we can see that there's a single layer hierarchy. So each indicator is loading directly to our objective. However, an example of an alternative framework would be using the SDGs as an intermediate layer, where each indicator loads to its respective SDG, and then the SDGs tie into the overall objective of sustainability. However, we won't be using this framework here. So next is the indicator values by mix. So we calculated for each of these mixes the indicator values for the 14 indicators, which I showed previously. Those values are shown here. Sorry, the units are cut off. But anyway, and we also have the statistical data here. So these descriptive statistics show the range and essential tendency and the variability between these mixed alternatives for each indicator. And especially a mean and standard deviation will be important for a normalization step later. Next is normalization. So as I mentioned earlier, we'll be using statistical normalization. So this is a z-score. So what we do is for each of the indicators, we convert them based upon their mean and standard deviation into what's called a z-score. A z-score represents the number of standard deviations away from the mean. So when we do this, then all of the indicators units will become standard deviations. And for each of those indicators, the value of 0 will be the mean, and then their new z-score will tell you how far away from the mean they are. And then we use t-score then to shift this to a non-negative scale of 0 to 100. Anyway, these are the z-scores and the t-scores for these different alternatives. And this also compensates for the directionality. So now for these z-scores and for these t-scores, higher value, closer to 1 means, this is closer to 1 means more sustainable, closer to 0 means less sustainable. Next, we have equal weighting, weighting scheme, equal weighting. So we may know a priori assumption about the relative importance of the indicators towards the goal. So we have the 14 indicators here with this single hierarchy framework and equal weighting. This means that the individual indicator weight, I'm sorry, this should be the point should be moved 1 over to the left here. The indicator weight is 1/14 per indicator. Now, one important thing to note, though, is that what we call here is equal weighting. It's not actually true equal weighting because it doesn't consider the actual data structure. And actually, some indicators may contribute more to the result due to their variability. Nonetheless, this is what we would call just like a general weighting approach. And now we come to the last step, which is aggregation method. We'll be adopting two different aggregation methods here. First is linear aggregation. So this is an additive operation, which allows full compensability between indicators. It's just basically a weighted sum, as you can see here. We apply a weight to each indicator value, and then we sum those up. Now, there are different aggregation methods. This is another one, which is geometric aggregation, which is a multiplicative operation. And geometric aggregation is less compensatory because the trade-offs are not equal. And in this case, we raise each indicator value to the power of the weight, and then we multiply all this together. Okay, so anyway, here's the results using the linear aggregation. What we have up here, this is the individual score. This is on a score of 0 to 100, a scale of 0 to 100. Shown here, these are the different alternatives. And then down here is the rank of each of these based upon their score. And so what we can see here is that the mix using blast furnace slag with normal aggregates, this mix right here, is judged to be the most sustainable alternative mix among these 6 alternatives. This is because, as we can see, the sustainability score is the highest among the 6 alternatives. However, the difference between this mix and this mix is 0.1, so it's actually quite small. We can see that the usage of blast furnace slag produces the highest scores, followed by fly ash and then OPC. And also we can see that for each of the mineral admixtures, or just for plain OPC, the usage of recycled aggregate actually has a negligible contribution to the sustainability score. Probably this is due to the trade-off is that high-grade recycled aggregates increase emissions because they require a higher energy input to produce. So their benefit in terms of reducing resource consumption is offset by the negative effect of the increased emissions. So that's how we can see that playing out in this sustainability evaluation. However, what we can see is that if we look just at the ranks, we see BFSNG is ranked 1, BFSRG is ranked 2. But the problem with looking at just ranks and not the original score is that actually the difference between these two is very small. So this is another thing to keep in mind, is that when we use a rank-based decision-making, is that it hides that underlying information about the distance between the alternatives. In reality, maybe we would say these two are equivalent because the difference between them is so small. Now, I also mentioned that we can use a different aggregation method, geometric. And so here we compare the results of linear aggregation to the results of the geometric aggregation. And what we see is that when we switched the linear aggregation to geometric aggregation, the individual scores of each of the mixes have changed. And this is because the aggregation method affects these individual scores, and it affects each mix differently because each mix has different characteristics. And what we also see is that previously in linear aggregation, the BFSNG was ranked number 1. With geometric aggregation, the BFSRG is now ranked number 1. So switching the aggregation method has resulted in a rank change, where now a different material is ranked number 1, a rank reversal, sorry. And so what this really illustrates is that in this process I showed, we have like these 6 different steps: indicator selection, data normalization, a weighting scheme, and aggregation. Now, if we choose these methods, these are methodological decisions, choosing which method to apply each of these steps. If we change these steps, the results will change. So this leads into my next topic, which I just want to end at the end of my presentation, is that these decisions that we make introduce methodological uncertainty into the sustainability evaluation, which means that the output of our sustainability evaluation is subjective to our decisions as the analyst as to what method we choose to calculate it. And since we don't have any standard approach, well, then this means that basically the analysts can choose any method they want. But there is a way that we can manage these uncertainties. Now, the reason why uncertainties arise in sustainability evaluation is 1, due to linguistic uncertainty, meaning vagueness about the concept, 2, lack of a framework, and 3 is data uncertainty. And so what this means is that there's a lack of specificity and systematization. There's some subjectivity in the evaluation approach, and so forth. So in the indicator-based evaluation, Well, the methodological uncertainty arises due to selection of inclusion of different indicators. The normalization methods which we choose, there are different normalization methods available. Subjectivity and weighting, and a mismatch between the weights that we apply and the actual intended effects. And finally, again, the subjective choice of aggregation method, which one we choose. And we saw that changing aggregation method changes the results, as I showed a moment ago. Now, if we just choose a single method for each of these, then what we end up with is a deterministic ranking or score, as in the previous demonstration. And this single value is highly dependent upon our methodological choice. So how can we handle this uncertainty? Well, we can do this by carrying out the sustainability evaluation probabilistically. And what we do is that instead of applying a single methodology, we apply multiple methodologies. And we create a probability distribution. And then we look at the uncertainty associated with the scores, or with the sustainability evaluation results of each value, with each alternative. And then we make a decision. Do we accept this level of uncertainty or not in our decision making? And so we can do this applying different analytical techniques, such as uncertainty analysis, which propagates the uncertainty from the input to the output. It allows us to see all the factors that cause variability and simulate all possible combinations of uncertainty. And then we can also apply sensitivity analysis to evaluate how much each of those inputs contributes to the output variability, using things such as a variance decomposition or global sensitivity analysis. However, it's quite complicated, so I'm not going to be getting into it here. So wrapping up, well, here I've tried to introduce some of the basic concepts which we need to keep in mind when we want to apply multi-criteria analysis to sustainable decision-making. In this case, I've talked about the sustainable decision-making for the decision of how to choose a most sustainable concrete mix. However, this framework is generalizable. We can apply it to any sustainable decision-making or any sort of decision problem. But for my parting message, what I would like to say is share this term as heterogeneous engineering. So heterogeneous engineering is this concept. Innovators need to focus on not only technical factors, but all resources necessary to create a seamless social web for innovation. Heterogeneous engineering, therefore, is a practice of creating networks which contain the people, skills, and artifacts necessary to achieve successful innovation. Now, this is important for us as concrete engineers, because when we are starting to tackle these sustainability issues, we don't have enough knowledge to do that as just concrete engineers. We need to reach out to other fields. We need to learn about multi-criteria analysis. We need to learn about sustainability. We need to learn about the environmental impact, social aspects, and so forth. And we need to utilize this information to solve the multidisciplinary problems which sustainability represents for concrete industry. So I hope today's presentation on multi-criteria analysis will be useful for you to think about sustainability in your work and your research in the future. So this wraps up my presentation. I'd like to say thank you all for joining. I'd also like to thank my former doctoral student, Dr. Joel Apone from Mindanao State University, Iligan Institute of Technology, for all of his hard work. If anybody listening, if you want to ask me some questions here, of course, but also if you want to talk to me about this topic or anything else, please feel free to email me. This is my email address. And also, these are a bunch of resources on concrete sustainability and evaluation with MCA that I have published over the years. And I'm happy to share this with you as well. Thank you very much for sticking with me.
Thank you very much.